So let's discuss thermal properties of materials. Let's begin by talking about one of the more fundamental properties that is related to thermodynamics, and that is heat capacity. Heat capacity is it's the capacity for for the material to store heat. Heat capacity is the QdT. So you can think of it as the amount of thermal energy stored per change in temperature. So for example, a material with a very high heat capacity can store a lot of thermal energy before it increases in temperature. And a material with a very poor heat capacity, if you put a small amount of heat in, you'll see this sudden increase in the overall temperature of the material. Talking about this differential, then we have dQ is equal to C dt. So we're saying the change in the internal heat in the material depends on the heat capacity times dt. Integrate, say 0 to Q. Integrate this from, say, temperature 1 to temperature 2. And this tells us that the change in, or the heat added to the material goes as, this. If C is a constant, then it's just going to be C delta T. But more often than not, the heat capacity actually is a function of temperature. At least at lower temperatures. So at lower temperatures, the heat capacity is a function of temperature, will look something like this. Now, once you get out to these higher temperatures, you can think of it as approximately linear with temperature, or even constant, depending on the window that of the temperature range you're looking at. These low temperatures are temperatures where we are seeing the initiation of different phonons. Now and we'll come back to that. This point here, theta D, this point is called the Debye temperature. EB. Now, the Debye temperature, you can think of it as the temperature where this heat capacity becomes linear. You can also think of it as the temperature in which all of the possible mechanisms for storing heat become activated. And there are a variety of these. Modes of energy storage. Well, one mode is through chemical changes or phase transformations. So you're taking water and you increase the temperature. When it reaches the boiling point, 100 degrees Celsius, that temperature stays constant as the water transforms from liquid to vapor, and then when it's become vapor again, then it can increase in temperature. What's happening is at that temperature, energy is being stored in the material via change in the local bonding configurations. The same thing can happen when you're having a polymorphic transition in a material changing from one crystal structure to the next. And these phase transformations, they're actually fairly, some of them can have a fairly large energy, a fairly large latent heat, but this is not what we're talking about when we talk about heat capacity. It is something that we do observe when we're measuring, for example, the absorption of heat, but it's not what we consider heat capacity. Now, what we do consider heat capacity is the promotion of electrons. And this is one of the predominant mechanisms for storing thermal energy in metals. So remember, we talked about energy bands, and I'm going to draw spaces in here. But we know that in a real system, which has an Avogadro number of atoms, that we have these bands, and they're extremely close together. And each one of them represents an electron state, and those electron states are occupied by electrons, meaning electrons will take those particular energies, and as we take these states, we know the number of valence electrons, or total electrons in the system. We occupy 2 per state until we come to the Fermi level. Well, as thermal energy goes into the system, something that can happen is electrons can get promoted up to these excited states, leaving empty states in the valence. And in doing so, there's a change in the energy. And we talked about this before, as this is a mechanism for increasing the conductivity of electrical conductivity of metals. In this case, we're talking about the energy that does allow that conductivity, and it being stored in the metal this way. So in metals, metals typically have a fairly high heat capacity, and the way that is achieved is through promotion of electrons. And this is active even at very low temperatures. Now, in the case of semiconductors or insulators, we do not have the promotion of electrons. Well, we can, but the energy is so high that it's going to be way over here. So what's happening in this regime, in ceramics and insulators and semiconductors, is we have energy being stored as lattice vibrations. Right? And I mean, just thinking about it at a molecular level, we know that these bonds, as you pull atoms apart, there's going to be a restoring force. So if you pull them apart and let them go, there's going to be some type of oscillation. The collective motion of all the atoms in a molecule, those are considered vibrational modes. In the case of a molecule, we call them vibrational modes. In the case of a solid, which has a crystal and periodicity, we talk about these in terms of phonons. In the case of, for example, water, we talk about these vibrational modes, and we'll have, say, oxygen and hydrogen, and we can have the hydrogen coming in like this, and the oxygen moving out. So we can have a situation where, if you will, our molecule is doing something like this, right? And this is called the bending mode in water. We also have a symmetrical stretching mode, in which the hydrogen come out and the oxygen goes up. So this would correspond to a molecule doing something like this. So that's and the third and final mode in water is called the asymmetrical stretching. And in this case, one of the hydrogen is going up, one is going down, and then the oxygen is moving off to the side. So you can think of that as going something like this. And this is called asymmetrical stretching. When we think about the energy versus displacement of atoms, we think about there being some type of spring between them, and it does something like this. R, where R is the separation. And then we can think of it as pulling these atoms apart. And they get pulled up here, and when they're released, then they go back and forth at the bottom as well, passing through the minimum and then going up and then back, because it's a spring. And in doing so, we've raised the average energy up by a small amount. So in the case of say water vapor, the water molecules will store energy by having these vibrational modes. In the case of crystals, they also have these type of phonon modes, but they are our collective lattice vibrations. Now, they are considered phonons, and we'll talk about that in a bit. The important thing here is that this theta Debye represents the point where all of these modes become active. So each of these modes, you can imagine that they have different energies. I mean, it takes different energy to take and to bend versus stretch the bonds. So this is the lowest energy, this is the middle, and this is the highest energy mode. So in the case of water, or water vapor, if you will, down here we have energy being stored being stored in a bending mode and then symmetrical stretching. And when we reach this point, all the available modes become active, and it becomes approximately linear. Now, in the case of a solid, we're talking about some lattice, and again, we can think about all of the atoms as masses with a spring. And I'm hopeful that you can imagine a situation in which a person, say, builds a model like this with, say, ball bearings and springs. And if they had some type of camera and they were watching it, and then say they hit this with a force, they pushed it or they jiggled it, you can imagine watching these vibrations here translate and shoot through all the crystal. But there's going to be a finite number of possible ways that the ball bearings or masses can displace, and those displacements are considered our phonon modes. Now these phonons are actually pretty amazing. These phonons, they can interact with electrons, they can interact with other phonons, they can interact with surfaces. They have a mass, and they have a momentum. I mean, after all, if you think excuse me, of an electron and a phonon coming in and then going off in different directions, well, we know that the electron has a velocity and it has a mass. That means then that the phonon, in order to change the direction of the electron, must also have a mass. And when we talk about the scattering, and we can actually measure the phonon modes by neutrons. So you have to go to a nuclear reactor, for example, at Oak Ridge, and you bombard the sample with neutrons, and you can look at diffraction patterns from neutrons in the same way that we talk about X-ray diffraction for measuring crystal structures. These diffraction of neutrons can be used to measure the energy and the excuse me, the energy and the periodicity of these modes. Another interesting thing is that these phonons are actually critical for some of the more interesting phenomena. For example, superconductors. Kind of the standard superconductor you think of, a metal, for example, lead. Lead becomes superconducting when you get down to, I think it's 5 degrees Kelvin. And the reason that it becomes superconducting is there is a coupling between electrons and phonons. So electrons, two electrons, which happen to have equal and opposite momentum, if they get within a certain distance of each other, they can exchange a phonon. And in doing so, they get tied together. And when they get tied together, they become what we call a quasi-particle, which is called a Cooper pair. And without giving you a lot of the details here, the amazing thing about a Cooper pair is that first off, it carries charge of 2 electrons, but it's also able to pass through other Cooper pairs and through the lattice without scattering. So when we talk about superconductors having no resistivity, so you can pass electricity through these without having any resistance, that's because we're passing the Cooper pairs, not passing electrons. Another interesting thing about phonons excuse me, is that electrons can create them. So it's not just a matter of interacting with them, but creating them. So if you imagine, for example, a lattice with positive nucleus, because all of our nucleus are positive, and at least to a certain extent, they're not perfectly shielded, and you have an electron that is passing through, say an electron here. As it passes through, and then this is particularly important if you have something where, for example, you have you're injecting electrons into a surface. You can imagine that there's going to be some attraction between that negative charge and the positive charged nucleus. And as the electron continues to travel, it has to be restored. So the nucleus, which gets slightly shifted, comes back and it starts to oscillate. And in fact, as this electron, say, passes along this path, what you're going to have is you're going to have a whole series of lattice vibrations that come out. And this is almost kind of like if you think about a wake from a boat, this is what you can imagine. So as this electron slows down, it's being slowed down because it's giving off energy in the form of lattice vibrations or phonons. So heat capacity then will have this general shape, have a temperature dependence. Above the Debye temperature, it's approximately linear. Below the Debye temperature, it has kind of a t to the cubed shape. In fact, this shape is typically approximated as 1 plus alpha 2 t plus alpha 3 t to the minus 2. Wow, this is some polynomial fit. There should be a t to the... Oh, minus 2, sorry. Minus 2, that's the plus 1. These are coefficients for fitting the shape of the curve. And kind of a final comment here about phonons and the Debye temperature. The Debye temperature is also a number that we use to qualitatively describe the stiffness of a lattice or the strength of bonds. So for example, diamond has an extremely high Debye temperature. And the reason for that is that the bonds are extremely strong, which means that in order to excite the higher energy modes, we have to have a lot of energy, a lot of heat going into the system at a high temperature. In contrast, something, for example, lead is going to have a smaller Debye temperature. And in general, when you talk to somebody, and if you say, well, how stiff is it? You could talk about, say, the modulus, or you could say, well, the Debye temperature is, whatever, 300 degrees Kelvin, right? The stiffness typically scales with the Debye temperature, and it also tells you about the melting temperature and the elastic behavior in general.